So in the last lecture, we have started a new iterating method, that is your fixed point iteration method. There we have done one example of x minus 4x, that you convert your root finding problem into your fixed point method. So we have started x minus 4x, the problem x minus 4x. So if you go for this, I have stopped it here at 7th iteration. If you perform it, it is going to this towards to this root up to your 20th at 20th iteration, you are moving towards your root. At 20th iteration, you will have accuracy 10 raised to the power minus 3. That means your 3 decimal places will be matched in the 20th iteration. So next we have started that how you can choose your g of x for the root finding problem. So for that we have done, that is your g dash x is less than 1, then you can say that it will converge towards your fixed point. So next is your existence and uniqueness theorem. So what it states is in the two parts, left
नहीं है नहीं.
So we have first part is the existence part, that is let, or we can say just only one part. Let gx be any continuous function let gx be any continuous function on AB and gx belongs to closed interval AB for all x belongs to AB. Then your first part is then G has at least one fixed point. G has at least one fixed point in AB. In the interval AB. And the second is if in addition G dash exists for open interval AB and there is a positive constant. There is a positive constant K that will be your less than 1 exists with the condition that your G dash x is less than equal to K for all x belongs to AB. Then there is exactly one fixed point. Then there is exactly one fixed point in AB. So this is your statement of your existence and uniqueness theorem. This part is for the existence and this is the second is for your uniqueness. So what it is saying that if gx be any continuous function on AB and your gx belongs to x open close interval AB for your all x that are in A and B, then definitely G will have at least one fixed point in your given interval AB. This is your existence. That means if it is to satisfy condition that your G is any continuous function on AB and your gx belongs to AB, then there will be at least one fixed point in the given interval. Moreover, if there is one more condition that g dash exists for the for open interval AB, and there is a positive constant k less than 1, such that this condition holds that your g dash x is less than equal to k for all x belongs to AB, then there is exactly one fixed point. That means there is the uniqueness fixed point of this. So the proof of this is, we are going towards the proof now. So if you see, you have what you are saying in your, that is your one line y equal to x, and you have some curve like this, you have g of x. So what are you saying? That this point is your fixed point. Suppose this point I am naming it as P. So if you see, this will be your P point and this is your GP. At this value, your GP and P will be same. So what we are actually doing, by your existence theorem, we are moving towards your bisection method. So firstly, we will take two guesses over here. Suppose I'm taking one guess as A, where your root lies, and one guess I'm taking as B, where your root lies. So suppose I'm taking it B. Fine. So if you take any 2 points, and if your GA is equal to A, or you say your GB is equal to B, then what happens? Then if you are saying GA is equal to A and your GB equal to B, then G has a fixed point. G has a fixed point at endpoints. That is A or B, then we are done and we have nothing to do. Then we are done and A or B are your fixed points. So if you choose a point such that your A is equal to G of A, or you choose any point GB is equal to B, then obviously you have found your fixed point, then A is your fixed point or B is your fixed point. So if neither this holds nor this, that means if GA is not equal to 0 and GB is not equal to B, fine, now we are taking this. Now then what will happen here? Now we will see. Now since the interval is AB, we have interval as AB, and A and B are not fixed points. Right? We are saying then in the interval A and B are not fixed points. So what will happen? Now since you have chosen a P is a fixed point between your A and B, because we are taking the condition that we have in given interval in which your fixed point lies. Now you are saying that neither your GA is equal to A nor your GB is equal to B. So what is the case left? So we have, in this case, GA will be greater than A and GB will be less than B. Is this step clear? Because you are saying A and B are not fixed points. That means if A is your not fixed point, that means GA is not equal to A. Is not equal to A, and you are saying that your GX belongs to AB. Fine. In the given statement, you have taken that GX belongs to AB. Now, since gx, this your gx is not equal to a, that means g of a will be greater than a. Fine. Again, your g of x is not equal to b, that means your gb will be less than b. So we can define a new function, but actually doing, we are moving towards, like we are treating it like for bisection method we have done, then we go for your intermediate value theorem. So we can define a function h of x such that that will be equal to your x minus g of x. We are defining a function hx, that is your x minus hx. Now if you set at this point a, so your a minus ga, fine, this is your function. You are saying your ga is greater than a, that means this will be your less than 0. So this will be less than 0, and if you have gb, gb will be b minus g of b is greater than 0. Why? Because gb will be less than b, because we have gx is belonging to your closed interval b, a, b, and we have the condition that we have here that gx is not equal to b, so it will be always less than b. So now your hx function, now x is continuous function, x is continuous function on a, b, and h a into h b is your less than 0, because this is your this quantity is less than 0, this quantity is greater than 0. So what your intermediate theorem says, by intermediate value theorem says, there exists a point, P that will belong to your interval a, b, such that hp is equal to your 0. This is your intermediate value theorem, that if you have a continuous function and you have ha and hp are of opposite signs, then by intermediate value theorem, like in bisection, so there will be a point in a, b such that hp equal to 0. If your hp is equal to 0, now since hp is my 0, which implies, what is your h function? P minus g of t equal to your 0. So you have in this case, which implies p is equal to gp, which implies p is the fixed point of gx. Is this clear? We are done up to part first, that there exists a point p. Fine, if your function is continuous and your gx is belonging to your closed interval ab for all x belongs to your closed interval ab, then g has a point p, fixed point p. Is it clear to all? So this is your existence part. Next, but we are moving to your second part, that is your uniqueness part. For uniqueness, let p and q be two fixed points of, let p and q be two fixed points of g x, let the points of g function, we can say, in a, b. That means now we are taking one point is p, one point is q. I am taking 2 points that are your fixed point of g. So if these are your fixed points, that means your gp is equal to p, and as well as gq will be equal to your Q, because your P and Q are your fixed points. Now we have also given a one condition. Now we have given one condition that my G dash is existing. Your G dash exists and your mode of G dash X is less than equal to K and your K is less than 1. This condition is given to you. Now if you can remember your mean value theorem, which you have done either I think +2 you do mean value theorem, that but your mean value theorem is that if you have f is any continuous function, if you have continuous function a or a and b and your f dash exists on open interval a b, then there exists a point c, then there exists a point C such that, but it is your f dash C is equal to what you say, your f of B minus f of A by your B minus A. This was your mean value theorem. So if your f is continuous and your f dash exists on your open interval AB, then there exists a point C such that this condition will hold. F dash C is equal to FB minus FA by B minus A. Now what we have open interval A and B. So by mean value theorem, and we are saying that there are 2 points, these are my 2 points P and Q. Fine. And then, but by mean value theorem, what we'll have, there exists a number. So by mean value theorem, there exists a number, we can say xi, between P and Q such that your G of P minus G of Q by P minus Q, that will be equal to your G dash psi. Is it clear? So this is your mean value theorem. You have 2 points P and Q, that, or since you are saying P and Q are fixed points, that means they are also lying in the open interval AB. That you say f is your continuous on AB and f dash exists on AB, there exists a point. That means there is existing a point psi. That means your GP minus GQ will be by B minus Q, that will be equal to your G dash psi. So now, if I take the modulus of P minus Q, now I know P and Q are my fixed point. That means I can write P as GP and I can write Q as GQ. So this will be equal to, by this one, we have this thing G dash psi into GP minus GQ. Fine. So this will be equal to your G dash psi and GP minus GQ. So you have given that your G dash is less than equal to your K value and your GP minus GQ, you can write that as P minus Q, because GP is equal to P and GQ is your equal to Q, because, and this is your, no, it will be P minus Q. Then you will have this GP minus Q, that will be equal to P minus Q. So G dash psi P minus Q, so you that will be less than equal to P minus Q. Now you are saying that K is less than 1. That means this quantity will be less than P minus Q. Fine. So now what you are saying, your P minus Q mode is less than equal to P minus Q mode. Fine. But but condition can hold over here. The condition only can hold over here. Here you can say less than. So you are saying your p mod of p minus q is less than mod of p minus q. That means our supposition, which implies our supposition is wrong. That is, p is not equal to q, which implies that your p is equal to q. Therefore, the fixed point, in closed interval a b is unique. So this is your uniqueness part. So if you have a function g of x, any function, and you want to find the fixed point, then if condition this is satisfied that your gx is belonging to your closed interval, then g will have at least one fixed point in AB, and if moreover this condition exists, then you have only one point in your given interval AB. So next is your example. So if you have example that is determine, show that g of x is equal to your x square minus 1 by 3 has a unique fixed point, on -1 to 1. So your conditions, all conditions will be satisfied over here. So when you will move towards your solution, what it is saying that x is belonging to your, now your x belongs to -1 and 1. For applying the above theorem, what it should have, that your gx also should belong to -1 to 1. So you can see from here, if you substitute the values, your gx will belong to your -1 to 1. And if you evaluate your g dash x, that will be your 2x by 3. And if you take its mode, g dash x, that will be always less than equal to 2 by 3, which is less than 1. That means your condition is satisfied. So by above theorem, G has a unique fixed point. G has a unique fixed point on, G has a unique fixed point on -1 to 1. How you can find the fixed point? You can take x is equal to gx. If you will take x is equal to gx, you will have in this case x square minus 1 by 3 equal to x. So you will have point x square minus 3x minus 1 is equal to 0. If you will solve this equation, you will have x equal to 1 by 2 3 minus root 13. That is your fixed point. That is the unique fixed point in your given interval -1 to 1. One more observation is over here, is that is remarks. You can say one more observation. Now, since you have solved it for the quadratic equation, so obviously there will be two roots. So you can check that G has also a fixed point. G has a fixed point. P, you can say other fixed point is 1 by 2, 3 plus 2, 13. But it is not in the interval -1 to 1. That is for the interval 3 to 4. So if you plot its graph, it will be like this. So you have a function like this. So this is your g of x, and this is your line y equal to x. This is your line y equal to x, and this is your gx. So you can see one fixed point is here in this, and one fixed point is here in this. So you have point -1 is this, and you have 1 over here, and this is lying between your 3 and 4. So one more observation is there. So this is one point and this is other point. Now at this point, your this x is also this and t of x will also be this. That means this point is your 1 by 2, 3 minus 2, 13, and g of x will also be your 1 by 2, 3 minus root 13. And at this point, you have value as 1 by 2, 3 plus root 13, 1 by 2, 3 plus root 13. So you can also observe here that we were saying in the theorem that your gx also should belongs to your AB for all x belongs to AB. Now, if you can see, however, in this case, if you observe, however, in this case, you have G4. If you evaluate G4, that is your x square minus 1 by 3. So that will be your 5. And G dash 4 is also your 8 by 3 is greater than 1. So even so, G does not satisfy the hypothesis of existence hypothesis of existence and uniqueness theorem. So even G does not satisfy the hypothesis of, but still G has fixed point. But still G has fixed point in the interval 3, 3 and 4 closed interval, which implies that your existence and uniqueness theorem, existence and uniqueness theorem is sufficient, is only sufficient to guarantee a fixed point, but not necessary. That means if you want to have a fixed point, these are only the sufficient conditions that guarantee that there will be a fixed point, but these are your necessary conditions. So you can see in this example, your 3 and you have 3, 4 closed interval. You don't satisfy your hypothesis of your theorem, but still you have a fixed point in this interval, that is your 1 by 2, 3 plus root 3, root of root 13. So that means if you want to fix point, that is sufficient to have these conditions to be satisfied, but these are your not necessary. Suppose you have G any function, you have any f function, it can have a fixed point, and it can be possible that it should not satisfy your hypothesis. So if you go for, so you have to check that for the unique, but if it is satisfied, the conditions are satisfied, then there will be definitely a fixed point, right? If your conditions are satisfied, then there will be definitely a fixed point. But if there is a fixed point, it is not necessary that the conditions are satisfied. Fine. So next comes from this, that is your contraction mapping theorem. That is your contraction mapping theorem, or you can also say that this is the convergence of fixed point method. Convergence of fixed point iteration. Here we will also find the order of convergence as well. So contraction mapping theorem, it states that it is in your 3 parts. We have done first part. Let G and G dash are continuous function, are continuous on your closed interval A and B, and Gx belongs to your closed interval A, B, for all x belongs to AB. Furthermore, let k is equal to maximum of, when your x belongs to open interval, maximum of g dash x, and this your k, the previous condition, less than 1, then you have first point as, which we have done the equation x is equal to g of x has a unique fixed point, p in the open interval a b. Fine. Second is the iterations or iterates, we can say the iterates p n plus 1 is equal to your g of p n and greater than equal to 1 converges linearly to p. That is your fixed point p. Third is the bounds for the error. In using iterates p and to approximate p are p minus p n, that will be less than equal to k raised to the power n 1 minus k p1 minus p naught for all n greater than equal to 0. Now this is your contraction mapping theorem. Based on your previous theorem that you have g function, g dash, and your gx is belonging to your closed interval AB, and there is a k, which is your maximum of g dash x, and when your x belonging to open interval and the value of k is less than 1. This we have done in your first theorem, that is your existence and uniqueness theorem. For that, you have to repeat, for the first part, you have to repeat your first part, that there exists a point P, like we have defined phi or h of x function, x minus hx. So it has a fixed point P and it has a unique fixed point by using your mean value theorem. Next, we are starting from here that your iterates P n plus 1 equal to Gpn, where here n is greater than equal to 1 converges linearly to p. That means we have a fixed point p over here, and it will mean the order of convergence. That means the order of convergence for fixed point iteration is 1. That means your linear convergence. Again, it can also become like this, that the statement that the sequence p and starting from n is equal to 0 to infinity converges to unique fixed point, converges linearly to unique fixed point. It can also be, we can also be write like this, the first two statements you can also write like this, that there exists a sequence Pn, because we are starting from the initial approximation, then we are doing this iteration. Pn plus 1 is equal to g of Pn, then the sequence of this will converge linearly to your unique fixed point. Next, your error bounds will be this. So by your existence and uniqueness theorem, by existence, and please don't write if it comes out to be in your exams. You have to prove this existence and uniqueness. You cannot directly write. By existence and uniqueness theorem, we have a fixed point, a unique fixed point, a unique fixed point P such that GP is equal to P. So by the uniqueness theorem, even by existence and uniqueness theorem, you have GP is equal to P. So next is since we are going towards second and third, that it is converging linearly. Since G, but we are saying you have a function Gx is equal to x, that means G maps AB, the interval AB into itself. But we are saying that G of x is equal to x. That means G is mapping AB interval into itself. Then the sequence defined by, we are defining the sequence, that is P. But we are saying P1 is equal to G of P0, P2 is equal to your G of P1, up to so on. Pn is equal to your G of Pn minus 1. That means this sequence, the sequence is defined because your function is defined. So your sequence is defined for all n greater than equal to 0, and obviously your Pn is belonging to your closed interval AB for all n. Why? Because we are taking the fixed first approximation, and then we are remaining in the closed interval AB. So how you define your error? Now, what you define your error bound is what you define error is that the difference between your Pn, that is the point at nth iteration, and your fixed point. We are saying P is a fixed point. So you have Pn minus P over here. You can write this as, because we are saying Pn, this is the sequence. If we are writing Pn is a fixed point, that means I have G of Pn. I am writing the sequence. Don't consider this will be equal to your G. This is your sequence. This will be equal to your Gpn minus 1. This is sequence. Because P is your fixed point, so it will be equal to your G of P. Now we have Pn minus 1 point. We have 1 point Pn minus 1, and we have 1 P. So again, this lying in interval A and B, so we can use G is your function given, and G dash also exists. So we can apply mean value theorem over here. So what your mean value theorem in this case? Gpn minus 1 minus Gp by Pn minus 1 minus P, that will be equal to your G dash psi, and your psi will also belonging to your AB. So you have over here G dash psi into Pn minus 1 minus P by using mean value theorem. So now this quantity is your less than equal to, given that it is less than equal to your K. So you have Pn minus 1 minus P over here. Obviously your psi in this is belonging to your closed interval AB, or since we are doing it for nth iteration, so I am writing it psi n for the simplicity. Fine. So this is for nth iteration. Now you can see at nth iteration, but you have Pn minus P is less than equal to K times Pn minus 1 minus P. So if you see from here, your Pn, K has come out, n minus 1 over here. So if I start with this over here, now if I'll take Pn, if I'll take Pn minus 1 minus P, the same I will have This is my g p n minus 2 minus g of p. Again, I can apply mean value theorem. So this will be less than equal to k times. I will have Pn minus 2 minus p. So proceeding in this way, we can do the iteration. That means this quantity, if you will take, this will be less than equal to k into k times Pn minus 2 minus p. This quantity is less than equal to k into k, Pn minus 3 minus p. And at the end, what you will have, this will be at the nth iteration. So you will have k raised to the power n. So if you see, you have n over here, you have n minus 1 over here, and the power is minus 1, and that is 1 over here. So you have minus 2 over here, so the power of k is 2 over here. You have 3 over here, so the power of 3 is over here. So when you will do this at the first approximation, you will read this is your p naught minus n. This you can write n minus n, so that will be your n. So in this case, we have, if we perform the iteration Pn minus n, that will be less than equal to Pn minus 1 minus p, that will be less than equal to your k square Pn minus 2 minus p. This will be less than equal to your k raised to the power n p naught minus p. Fine. So now, since what we have given, since we have given that your k is less than 1, which implies if we take the in the limiting case, when your n is tending to infinity, your kn, limit of k raised to the power n, that will be equal to your 0. That means when in the limiting case, when n is tending to infinity, pn minus p, what I will have, that will be less than equal to limit n tending to infinity, k raised to the power n, p naught minus p. So this quantity will be equal to your 0. That means, which implies your sequence pn. But we are saying that mode of value something is less than equal to 0. That means limit n tending to infinity, your pn minus p is your 0. That means your limit n tending to infinity, pn converges to your p, which implies your n p, the sequence pn converges to your p. So we have shown that the sequence is convergent. So next, what we have to find? We have to find the order of convergence. We were saying that convergence is linear. So if you see from here, so you have over here that your pn minus 1 quantity, name this as 1 equation, and name this as, we have this equation. Now this implies p limit pn minus p is less than equal to, I will explain you 3 example. Pn minus p over here is pn minus p, we have k raised to the power n. Somebody has sent me that repeat. When it will complete, I will repeat that example. P naught minus p. So I have named this equation 2. So by 1, what we have by 1, we have pn minus p is less than equal to your k times pn minus 1 minus p. So if you can write in this way, fine. Pn, what will be your pn plus 1? If you proceed like this, pn minus p less than equal to your, but it will be your k times pn minus p. You have pn minus p is less than equal to k pn minus p. At n plus 1, you will have pn minus p over here. So what you say, this is your error at your n plus 1th iteration. At n plus 1th iteration, what you say, your value minus your exact value. This is your value. So you have en plus 1 is less than equal to k. So this is the error at your So this is your error at your nth iteration. So you have en plus 1 is less than equal to your k en, which implies your en plus 1 is proportional to your en because your k value is equal
मैम
to yes.
मैम एरर तो दो कॉन्जिक्यूटिव के बीच में होएगा ना. अब pn प्लस 1 और माइनस p वो
How we
ज्यादा
have
दूर.
defined the order of convergence? How we have defined the order of convergence? Order of convergence, if you remember in the last yesterday's lecture, we have defined that xn plus 1 if your root is alpha, fine. This we have defined, this should be equal if it comes out to be c into xn minus alpha, fine. So you have defined this is your asymptotic error constant. You have defined the error at your n plus 1.
ओके मैम.
So
ओके मैम.
you are approaching towards your root. Here your root is alpha, but here your root, that means root is something, we are talking about your fixed point. So p is my fixed point, that is my root, we can say. So that is the error, will be very less. So en plus 1, that will be less than k, and k is your less than 1. So that means here I have the value, if there 4, t over here is 1. So fixed point iterative method, fixed point iterative method converges linearly, fine. So this was your second part, that it has convergence linearly. The third you have that the error bounds for this. Now you know that we can write for the error bounds. We can write now. If you say, if you have taken any approximation, you can take p minus p naught, fine. So here you can add and subtract 1 point. So by triangular inequality, what you will have over here, p minus p1 plus p1 minus p naught. This is your by triangular inequality. If you have mode of a plus b, that you have less than equal to mode of a plus mode of b. This is by triangular inequality. Now we are using here 2. How we are using 2? You have said that your pn minus p is less than equal to your k times, but you do over here pn minus 1 minus p. So if you have 1 over here, you can also write this as p1 minus p plus p1 minus p naught over here. So this p1, if you take it over here, so this will be less than equal to k times, here n is subtracting, so this is p1 minus 1, that will be your p naught minus p plus p1 minus p naught. If you take this term towards this side, or you can also write this as p minus p naught, because this is in the mode. So you will have 1 minus k times p minus p naught less than equal to your p1 minus p naught. Then you will have p minus p naught is less than equal to 1 by 1 minus k p1 minus p naught. You multiply k raised to the power n both sides. You will have k raised to the power n p minus p naught less than equal to k raised to the power n 1 minus k p1 minus p naught. Now this quantity p minus p naught, obviously this quantity is less than this. So we have now what we have, Pn minus p. If we start for the Pn minus p, that was less than equal to your k raised by 2. By 2 we have this Pn minus p, that is less than k raised to the power p minus p naught, and this quantity k raised to the power n p minus p naught is less than equal to your k raised to the power n 1 minus k p1 minus p naught. So these are your error bounds, that your absolute error will be less than equal to this. From here you can also find your number of iterations that we will do in the next class. So these are your error bounds for your fixed point method. So this was your contraction mapping theorem. Firstly, we have done existence uniqueness theorem. Then we have proceeded towards your convergence linearly. Then you can go for your error bounds. Drishti wants to ask about how we have, please explain your root 3. So we have over here, we have to approximate x is equal to root 3. So this was the question when we have to approximate x is equal to root 3. So the question was for approximating the root. So you have a function x square is equal to minus 3. Now we have to use fixed point iteration method. That means you have to convert your problem, root finding problem, into your fixed point problem. So you can convert your f of x into x equal to gx form. This you can done in numerous ways. So we have taken 3 examples for the same, in which you have taken, this was your function, you have added over this, then you have taken g of x as this. So you have x is equal to g1 of x, g1x is this. Second, you have x square equal to 3 of x, 3. You can also take it x is equal to 3 by x. So you have one, we have taken one this example. Again, we can also do this. We add this. So when we have performed the iteration, so for G1, it is not converting, it is going far from the root. For G2, it is oscillating between 2 and 1, 5. G3, that is your, it is converting towards your root. So that was your sufficient condition. In this case, you have G dash of x is less than equal to k and your k is less than 1. You can check for all well for x. If you take any interval, you have started from initial approximation 2, and if you start it from 1 to 2, the value of this will be less than equal to 1, will be less than 1. So you have all condition, and your gx is also belonging to your 1, 2 interval. So in this, the conditions are not satisfying, that you can check. So you have to choose that function whose derivative mode is less than 1. So that is your sufficient condition for having your fixed point that we have discussed, that if you have g dash x that exists, and if it is less than k and your k is less than 1, then definitely there will be a fixed point. So I'm stopping it here. We will continue this example in the next lecture. If you have any doubt, you can ask. Drishti, is it clear?
Yes, ma'am. Ma'am, how have you calculated the values g1, g2 by simply putting the x value?
I am also saying that you can take gx if you have any function f of x is equal to 0, you can transfer it in, you can reformulate this in numerous ways. There are so many ways, but the best gx will be that if it satisfies the condition that your gx is belonging to your closed interval and your g dash x should be less than equal to k and k should be less than 1. If you have this condition, then your chosen, which you have chosen g of x, that definitely converges to your root. if it is set. That we have done in your existence and uniqueness theorem. There are numerous ways, like I have already told you, x tan x. Fine, you have suppose quotient x minus tan x equal to 0. You can also do it x is equal to tan x. This is one way. Fine. You can do also x is equal to tan inverse x. This is the second way. You can also do 1 by x is equal to 1 by tan x. Then you have over here, then you can add in this x plus 1 by x is equal to x plus 1 by tan of x. You can choose one way, this 1 by x plus x plus tan 1 by tan x minus 1 by x. You can also choose this interval. You can choose so many x, but you have to choose that gx which satisfies this condition, so that it will surely give you a fixed point P in the interval a b. We will do its example in the next class. So there will be your gx that you have to see. Gx you should choose for evaluating your root. For evaluating your fixed point, that fixed point will be your root. Is it clear?
Yes, ma'am.
Okay, I'm
Yes,
at
ma'am.
next class. I will upload this on Drive. You can access from here. Okay, thank you.
Thank you, ma'am.